All right. Audio good. Yes, yes, yes. All right. Let's change this cam. All right. So we are back finally. Like I said, sorry about that, guys. Good reasons. I had to go save some friends. But nonetheless, sorry it's taking a second. Even just before that to kind of get back to this. But nonetheless, so we want to look at this set of lectures, this couple lectures is going to be for the stuff in 3.3 and 3.4. But we want to look at what we just ended with in the last section. So by the time you're through 3.2, the big thing that we figured out, among other things, but one of the big things we figured out is um, we already knew how to find the mean of a distribution. The big thing we figured out was the standard deviation. And that gave us an idea of a way to measure and talk about and analyze the spread of our data. And one of the things that we saw at the end of that last lecture is that saw what was it, the empirical rule. So we saw this idea that not every distribution ever, but a lot of distributions do end up, a lot of distributions of data do end up looking like a bell curve, right? And if it's a bell curve, then my mean, so if it roughly is like a bell curve, then my mean is roughly in the middle. So that would be my mean. What we saw then is you can kind of count off standard deviations. This is kind of one standard deviation, say to the left, minus one standard deviation. That's minus 3 standard deviations, etc. And we can count off standard deviations to the right as well. So if it's roughly bell-shaped, then my mean is basically in the middle, and we can count off standard deviations to the left and the right. And so what we saw at the end of that last section was if it's not bell-shaped, we have Chebyshev's theorem that allows us to kind of say, well, a certain percent of data at least is within so many standard deviations of that mean. But then we saw the empirical rule. So, and the Chebyshev's theorem, the nice thing about that is it worked for any distribution. But if you know you do have a Bell distribution or roughly a Bell distribution, roughly a normal distribution, then you could refine those percentages. We could say that 68% of our data, actually just about 68%, was between one standard deviation above or below the mean. And then what was it? 95% of our data was between two standard deviations above or below our data, the mean. And what was it? 99.7% was 3 standard deviations above or below. So we saw that the standard deviation, besides just being in general a tool, right? A measurement for how spread out the data is, and a pretty good tool at that. It ends up being then a really good tool for analyzing the percentage of data that falls kind of left or right, kind of basically in a middle chunk of the graph, left or right of that mean. So what we're going to look at today is, so like I said, the standard deviation ends up becoming a good tool for measuring percentage of data left or right of our mean. It also just in general gives us an idea of spread. It also is a good tool for essentially measuring position of data. So what we're going to talk about, you'll see what we end up talking about in all the lectures for 3.3, 3.3, and 3.4 is we now want to think about this idea of if I've got some data, some piece of data from my overall sample or my overall population, we can get an idea of its position kind of relative to the mean, essentially. So let me give you an idea of what I'm trying to say here. So what we're about to look at, what's called the z-score, but what we're about to look at, it only applies to Bell distributions. The yeah, only applies to things that are roughly Bell distributions. So you're going to see as we go throughout this, not just this section, but throughout this course, they're going to let you know whether you can assume roughly that that data is from roughly, it doesn't have to be exact, but pretty close to a Bell or a normal distribution. Or you're going to see some problems where you're going to have to go ahead and graph the data first, and then you can see for yourself. From the graph, whatever type of graph that you do for that data, you can see for yourself that it is I call it roughly a Bell distribution or normal distribution. So if I have a Bell distribution, then just like we saw at the end of the last episode, just like we saw at the last end of the last lecture, my mean is roughly in the middle, and I can count off standard deviations above or below. So if you think about it, then standard deviation is kind of becomes a general is not the one word for it. It's not the best word, but so also let me stumble and find the words, but we'll start with general. So it kind of becomes a general way to essentially measure how far something is away from the middle. It's one standard deviation, it's two standard deviations, it's three standard deviations. Now maybe it's not just a whole number, maybe it's half of a standard deviation, right? So half of a standard deviation would be roughly here. 1.5 would be here. 2.9 would be here. So we can think of something being 2.9 standard deviations above the mean. That would be roughly here. So the interesting thing then is, if you think about it then, again, so this picture is general, right? I haven't given you any data. There's no context. We don't know what we're talking about, right? We don't know if we're talking about people, time, I don't know, medicine that somebody's being given. Like, this has no units of measurement. It has no problem that's associated with. It's completely abstract, or it's completely general. But what that means is, if I have any distribution that looks like this, what I'm saying is then, in general, no matter what the context is, I can use the standard deviation as a way to count position, basically. Count how far something is above or below mean. So it's almost as if the mean, so literally, not only almost as if, it's as if, or it's just like, now can treat this, the horizontal line here, whatever the units would have been for the problem, right? So whatever way that you have actually marked out the horizontal line for the data that we're looking at, instead of that, it's as if the mean is 0. So it's as if the mean is the middle of just a plain old number line that you guys have seen since like forever, really, like 6th grade or something like that. So it's as if middle is 0. And if the middle is 0, then one standard deviation above it, we could treat that like a 1. So literally we can call this 0, and we can call this 1. We can call this, so then what would we call this? That's 2. So literally you're just dropping the standard deviation symbol, but we're keeping the same meaning. We're saying that, so this position is one standard deviation above mean, which is 0. This position is 2 standard deviations above the mean, which is 0. That would be a 3. So then what would these positions be in terms of their standard deviations? That would be -1, that would be -2, that would be -3. So we can, the positions on the horizontal line here, on the number line, for the distribution, instead of whatever unit of measurement they're talking about, and whatever our data is, we can mark these positions by the mean being 0, and then the rest of these just being the distance away from 0, but using the standard deviation as sort of your distance, the way you're measuring distance. Again, so we're saying that basically we can say effectively that that's 0, that's 1, it's 2, That's 3. It's -1, -2, -3. This way of reading number line for your distribution, this way of reading your data, reading it using the standard deviations instead of whatever the units are for your actual data. This is what's called a Z, so they call this a Z-score. Call this a Z-score. And we're gonna see as we do some problems, it's actually hella useful. We're gonna see not just in this section, we're actually gonna be using Z-scores going forward in this class a lot. It is hella useful. Because again, one of the nice things about it is I can get an idea of the position of a piece of data that I have in this distribution. So whether it falls way up here, way down here, pretty close here, pretty close there, I basically can have a number from that number line for it. So I can have a Z-score for it. It gives me an idea of the position that data is in compared to the rest of the data we're looking at. And again, the nice thing here is we don't know what this data actually is, right? So I can have a Z-score for any bit of data from any context, for any experiment, any data set that we've ever run, whether it's in psychology, business, economics, it doesn't matter. We can have a Z-score for that data, which means we can start to compare data from one data set to another because we can compare them with their Z-scores. In some sense, their Z-scores allows us to kind of like standardize everything so that we can kind of compare data from now multiple sources, not just within one source, to get an idea of how does it stack up against the rest of the data? How does it stack up against each other? Where is its position compared to the middle, the mean, etc. So now I think visually it's easy to kind of see then what the Z-scores would be for, for data we're looking at as long as it fits standard deviation. So we need a way to basically turn what I've just described to you, this number line that's based on standard deviations. We need to basically turn that into a calculation that we can do. So give me a second. Actually, give me a second. Let me drink some coffee, get some inspiration here. All right. Yeah, so my Z-score then is just my position along this number line. So again, like I said, if my Z-score was 0.25, then I would be a quarter above my mean. And if my Z-score was -1.5, then I would be 1.5 standard deviations below my mean. So we got to find a way. So to get our Z-score, then we got to find a way to basically figure out how far my data is either above or below my mean. And then I've got to count or measure it by the standard deviation. So think about kind of the ideas there. First, you need to find the distance it is away from the mean, whether it's positive or negative. And so we've talked about this a couple of times in this class so far. If you want the distance one number is from another, what operation do you do for that? Good. You do subtraction. So the distance from one thing to another or one number to another is always subtraction. So whatever, again, so we're gonna, right now this looks just abstract to you, but we're gonna get some problems where we actually have some numbers to play with. But even before we do that, and even without that, so I give you some data that's right here. First thing you gotta be able to do is how far is it from the mean? So you gotta, whatever that data is, you gotta subtract the mean from it. So the Z-score, you start by taking whatever your data is and subtract your mean. And then we want to measure by, so it's like we want to break up our number line into standard deviations. We want to measure by the standard deviation. So whatever that distance is away from the mean, if you divide by the standard deviation, that's gonna give you the point on the number line that you're at. So to get your z-score, you do x, so you do your number minus the mean, you divide by the standard deviation. That gives you your z-score, but like I said, don't don't memorize this as just some abstract equation. Z-score is your position on a bell curve. It's your position above or below the mean, kind of on this number line, based on your standard deviation. So we'll look at some problems. We'll literally look at some problems for how to play that out. But again, notice that this becomes not only this becomes a super useful way to show and measure position of data, because as long as your data is roughly bell shaped, and as long as you can calculate a mean or a standard deviation, which we know we can now, then you can do this for any data that fits, period, end of story. So every single experiment, bits of data that we grab, again, from economics, psychology, sociology, chemistry, physics, etc., whatever, we can now have an idea of that data's position compared to the middle of that data, using this thing called a z-score. And all it requires is a mean and a standard deviation, which again, we saw in the last section. You can calculate, well, we saw in the first chapter, you can calculate a mean for any bit of data. And we saw in the last section, you can calculate standard deviation for any bit of data. So we have no problem. You can calculate a z-score for any bit of data that fits a Bell distribution ever, because we always can calculate the mean and the standard deviation. Good. All right, so let's take it from the abstract and see kind of how useful this is. Let me decide whether I want to do that or I want to review the data, write it down. I want to project. And let's project them. And let's change this to and that's what supposed to be in there. About them. Let's look first at a 10. All right, so let's kind of practice this idea. So in 10, it says they call this the age of senators. So the age of senators. Senator sounds like the senators taking over the republic or something like that, which um, may not be far from now. So here it says the average age of senators in the 114th Congress was 61.7 years old. So actually, I should have checked before started this video. I don't know which Congress this is. It wasn't published too long ago, so this is at least pretty recent. So in the 114th Congress, the average age or the mean age was 61.7 years. If the standard deviation was 10.6, I'm the Z-score of a senator who is 48 years old. And one who's 60 was 6 years old. So let's look at these two. So again, I want to keep this picture up here though, because again, I mentioned in the last video towards kind of the back half of the last video, you're gonna see as you keep going that these diagrams that I'm kind of having you guys, that I'm writing up here and I'm asking you guys to create, you're gonna see that these pictures are actually really integral for you figuring out the problems. I have seen statistics students just try to do everything by formula. And I'm not saying that there aren't people that works for, but there's not many. And this is not because of people's abilities, it's not because of people's smartness. It's actually just brain wiring. Not many people actually, their brains don't, for most people, their brain is not wired to just rely purely on words and formulas and just like an accountant, just let me just crunch through things and roll it out, right? So if you've been trying to do that and finding that it's hard, there's probably a good reason that it's hard. It's not because you're not able, or it's not because you're not understanding what's going on. It's because your brain doesn't work that way. Most people's brain doesn't work that way. Some people like me are kind of on the other side of the spectrum. There's many different spectrums, but the other side of that spectrum where I'm very visual, I honestly can almost visualize everything that we're doing without ever writing it down. So my brain is the opposite of a procedural, what do you call it, equation or formula oriented brain. I can just do everything in my head and see it. And so I do everything with pictures. Not many people are like that either. Most of us are in the middle. Most of us kind of actually, guys, most of us are in the middle, right? So this goes back to, I've been telling you guys this Bell or normal distribution, lots of sets of data. When you aggregate them, they end up looking like this. A lot of things that we study for humans, psychology and sociology, traits of humans, ways we learn, blah, 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 whatever it is. Um, you know, like whatever those traits are that you're studying in psychology or sociology, a lot of times, a lot of times, you end up with a normal distribution. So all these things that we kind of talk about, with people and their abilities, or all these spectrums that we talk about. The reason that they're a spectrum is because when you aggregate everybody data for everybody and how they experience things and act in the world and etc., you almost always end up with this. So that means you're always going to have a bunch of people in the middle that we call normal, but that's really a misnomer, right? There's no normal, right? There's a bunch of people in the middle that all act roughly similar. There's always people, both sides of the spectrum, always people that like their abilities are down here compared to everybody, or their abilities kind of go on this side of the spectrum compared to everybody, and other people whose abilities are on this side of the spectrum. Always. So what I'm saying is that is a facet of humanity, because every time we study any human abilities in any way that you want to look at it, almost always end up with this distribution. So that means there is no normal. There's just majority of people are wired, usually wired pretty similar to each other. Then there's always people that are wired left and wired right. So getting back to what I was just saying, there's going to be a couple of y'all that are really good with just running formulas, and there's going to be a couple of y'all like me that are really good with just picturing everything and basically doing all your work in your head. But most of you are going to be in the middle. Most of you are going to do a combination of formulas and visuals. So where I was trying to get to before that was so that's what I'm saying. Most of you are going to be a combination of visual and formula. You cannot do everything with formula, and you can't do everything with a picture. You need both to kind of marry and, kind of feed each other and work with each other. So if you've been having trouble doing a lot of this work by just trying to memorize the formulas and bash them out, again, there's a reason. The reason is you need a picture. So that's where I was trying to get to with all this, but a lot of good points along the way, very true points. You need a picture. So that's what I'm saying. For most of you, you need a picture. So when you're doing these problems, even a problem like this, where it just gives you a bunch of words and numbers, what I'm saying is you should not do this problem without a picture unless you absolutely can just run everything with a formula. It's not going to be most of us. You should draw this picture so you can get an idea of what these numbers that they're talking about, kind of what they mean spatially. So anyways, yeah, so that's the big point I wanted to get to, besides all the really good little points along the way, is you absolutely should be drawing a picture. I was saying it at the end of the last lecture as well. You absolutely should be starting to draw pictures for every problem that you're doing. Now that we're looking at, we have standard deviation and we're looking at where things are in our distribution, because it's going to be really hard to analyze and do these problems without it. There is, in a college algebra class, you would get a question like this where it's just words and numbers, and they would teach you how to to analyze it, to look at this is the number, and this means subtraction, and this means X, and you would write an equation, you would solve it. What I'm saying is that statistics is different than that. When you read this, you would never be able to turn this into an equation. And again, not because of your ability. Y'all are smart. You're going to pass this class easily. It's not because of your ability. It's because the way that's written is not designed for you to read it and interpret it as numbers and letters and write an equation. It's just not written that way. It's not written like a college algebra question. So in order to figure out what we're gonna do with this problem, you need to start by what I'm gonna do is I'm gonna put these numbers and I'm gonna start to interpret what they're doing in terms of this picture. This is where I'm saying if you don't have the picture, then this problem becomes really hard to do, not because the math is hard. You'll see the math is actually really hella easy, but you're not gonna be able to read an equation from that. You need the picture to tell you the equation and to start doing that work. So, okay, anyways, I think I'm on my soapbox too much. Anyways, so the average age of senators in the 114th Congress was 61.7 years. So let's pretend this is the 114th Congress. This is the 114th Congress. Says the average or the mean age was 61.7. So where is that 61.7 on this diagram? That 61.7 is in the middle. That's my 0. This is 61.7. So then they say the standard deviation is 10.6 years. That means, for instance, one standard deviation above mean is this plus 10.6 years. Then this is gonna be plus 10.6 again, etc. So just like I was kind of writing and we were seeing on the last lecture. That means one standard deviation below mean is going to be 61.7 minus 10.6. Two standard deviations is another minus 10.6, etc. So what we're trying to get to with the problem is saying they want you to find the z-scores of a senator who's 48 years old and one who's 66 years old. So like I said, z-score is about position. So they want to figure out where on this number line corresponds to a 48-year-old senator, where on this number line corresponds to a 66-year-old senator. So the way we're going to do that is with this z-score formula. So let's start with the first one. The first one is a 48-year-old senator. So first of all, again, think about, just look at it in your diagram and at least get an estimate. 48 years old, is that above or below 61.7? That's below. So 48 years old is going to be somewhere here, somewhere left of 0 along the number line here. You can already see You do 61.7 minus 10.6, that's gonna be 51 roughly, and then minus another 10 is 41, so it's gonna be somewhere between -1 and -2. Now, saying somewhere between -1 and -2 is not enough. That's a guesstimate. It's a really rough guesstimate, but it's way far from being exact. But for the 48-year-old, my distance, so again, the way I calculated z-score, so the way 48-year-old, to figure out where along that number line it is, what the z-score it is, first you gotta figure out how far is it away from the mean. So we're gonna do 48 minus our mean, which is 61.7. So I'm literally just plugging into this formula the information they're giving me. So 48 year old senator, subtract the 61.7 to figure out how far you are away from that. Notice that this is the same thing. This is the same little calculation that we did for standard deviation, the deviation part of it. How far is it away from the mean? So this is just that same deviation calculation that you guys did for standard deviation. But more than that, I'm not even gonna have to think that serious or that detailed. It's just the distance away from 61.7. So 48 minus 61.7. Then we're gonna divide that by our standard deviation because we're counting, essentially we're counting by 10.6s. That's 1 inch. One way to think about it is 1 foot or 1 inch on this ruler is 10.6. We're trying to figure out how many feet you are away. Maybe that helps make sense. But basically, I just plug in my standard deviation and we are going to run that calculation. The one thing that this problem is not saying is where you round. Usually a rule section for the rounding. Give me a second. Let me see what argument. I would round 1 extra decimal place, but I don't know if that's their standard rule. Like the 10. All right, so for z-scores, we're gonna automatically round to 2 decimal places, and you'll see why when we get later in the course. So these z-scores, later in the course, we're really gonna study normal distributions, like, so any sample or population that comes from a normal distribution, from a distribution like this. And you're gonna see we're gonna have what's called a z-score table, and that table is always rounded to 2 decimal places. So because of that, to get us prepped for seeing it that way, we're gonna round this to 2 decimal places. So that's a calculation we can do. So that's from here, this is straight calculator. 48 minus 61.7, whatever that is, divide by 10.6, and then only at the end do you round to 2 decimal places. So we don't even have to pause for this. Just take a second and run that calculation and let's see what we get. It's the clock. It's not the calculator. You subtract here, you're gonna get negative 13.7 on the top, and then we're gonna divide that by 10.6. So what you should end up getting roughly on this is negative 1.29. Oh, seriously. That's what's this. So this ends up being roughly negative 1.29. So the z-score for a 48-year-old senator in the 114th Congress would be negative 1.29. So a 48-year-old senator would, on this number line or in this distribution would be roughly somewhere about like that. That's a 48-year-old senator. So again, notice that now, so having this z-score, I now can place, in this case, my data point, 48 years old, in this picture, in this distribution, and you now have a really good idea of sort of where it sits. Therefore, you can make some analysis and some comparison with some other data you see, right? Without the z-score, you wouldn't be able to do that. You just wouldn't have an idea of position. So again, that's what z-score is about, is position. Position in a Bell or normal distribution. And they also wanted the z-score for a 66-year-old. So you guys should be able to calculate that then. Just figure out the distance away from the mean, that's the top of your fraction, divide by the standard deviation, figure out how many of those you are away, and then round to two decimal places. So this one, I'll give you guys just a second to do. Go ahead and pause on your side, I'll pause on my side, and figure out the z-score for the 66-year-old. Sweet. So for the 66-year-old senator, seconds. All right, but the calculation, easy enough. So our z-score is gonna be 66 minus 61.7. We're gonna divide that by 10.6. That part is what, 4.3, so it's gonna be 4.3 divided by 10.6. Probably roughly 0.42 or maybe even 0.43. Let's see. Sure I got that right. Yeah, 4.3 divided by 10.6. Oh, slightly smaller. So to two decimal places, that's going to be approximately 0.41. So the 66-year-old senator is the z-score is 0.41, so they're located almost halfway between 0 and 1 there, so maybe roughly there. That would be a 66-year-old senator compared to all the senators, the population of all the senators from that 114th Congress. So we can calculate these position scores, these z-scores, for data that fits a Bell or normal distribution. The next thing we want to do with this, so that's the first thing you need, is just to be able to calculate those z-scores. If you think about it, then we should be able to sort of do this in reverse. We should be able to look at a z-score and basically work this backwards to tell us what the what do you call it, what the data point is. So this problem, I gave you the data point, so you plugged it into the equation, and I gave you the mean and I gave you the standard deviation, and you calculated a z-score. So the next problems we're going to look at is we're going to go backwards. We're going to start with the z-score and calculate our way or work our way back up to what the data point is. So let's look at problems like that. So let me keep that equation up there though, we'll need that. So let's look at teacher salaries. So the average teacher salary in a particular state is $54,166. Usually when they're referring to teachers, they mean K through 12 teachers. And that's probably pretty darn accurate. I mean, it's probably pretty mid, or not just a state, but I'd say it's probably mid for the US basically. So the average or the mean teacher's salary in a state is 54,166. If the standard deviation is 10,200, find the salaries corresponding to the following z-scores. So again, let's write some numbers down. Let's start, take these numbers and at least get an idea of what they look like in our picture so that we can use our formula and get an idea of the answer here. So let me erase these again. So now my mean is 54,166. And one of these standard deviations is plus or minus 10,000, 10,200. So let me just write that there. So plus 10,200. So let's go with, we'll do A, we'll do a couple of these. So for A, our z-score is, well, actually, let's not do A. These ones you technically could do without the formula, but let's do part D here and part E. So part D, my z-score. So here, let me just write this out because it's partially covered up. My z-score is 2.5. So we want to figure out what salary would be 2.5 standard deviations above my mean, above 54,166. Hey, give me a second here, actually. Well, let's talk about a way to solve this. So I'll say actually, I mean, you need the idea of the formula here, but you actually don't need the formula. So let's kind of talk about, again, the idea of our formula is, our z-score formula is the distance away from the mean divided by the standard deviation. But what it tells me, so if my z-score is 2.5, what I'm saying is, again, I'm 2.5 standard deviations above the 4,166. So can you think of a way, some kind of, just simple calculations to figure out what would be 2.5 standard deviations above 54,166? So maybe it makes sense to you. Hopefully it does, that instead of doing a complicated, so we could plug numbers in and what you'll end up doing is some equation solving, but it ends up that you don't even really have to do that. We are 2.5 standard deviations above 54,166. So the first thing you need to do is just figure out what is 2.5 standard deviations. My standard deviation here is 10,200. So what is 2.5 times 10,200? That's how much I am going to be above my mean. So what is 2.5 times 10,200? Let's do that really quick. And when you multiply that out, you should get, I think it's 20. Let me make sure I'm right here. 400 and then 5,100. So it should be 25,500. So this person's salary is 25,500, but that's above your standard deviation. Or your mean. So then to figure out their salary, what would I do with this? Good, I just add it to my mean here. So then we can just take that and add it, 54,166. And what does that give you? Again, we don't even need to pause, just calculate that really quick. So what are you getting there? So you should be getting 79,666. So for part D here, a z-score of 2.5 corresponds to a salary of 79,666. Which I literally don't think I've ever met a K through 12 teacher in my life that makes that much money. So remember that we said the empirical rule says that as long as your distribution is Bell or normal like this, that 95% of your data, right, fits two standard deviations above or below the middle. And so we're well beyond that. We're 2.5 standard deviations. So we're more on, let's see, said 3 standard deviations was 99.7% of data. So 2.5 is probably something like 98%. So what I'm saying is basically this person makes more than 98% of all teachers. Which, yeah, so like I said, that's why I've never met anybody that's made that much money. I've also done all my K through 12 teaching. Well, not just all my K through 12 teaching is in Texas, and I think a lot of the people that I know that teach either teach in Texas or Florida or Georgia, a couple in North Carolina. North Carolina pays their teachers well, but Texas, Florida, Georgia doesn't pay their K through 12 teachers well. They pay them well below sort of the national average. So you live in a big city, so like San Antonio right now, 54,166, that is probably the average. But if you take the average all over Texas, nowhere near. The average in Texas is probably 45,000. I would be willing to bet. So a good, actually almost 10,000 below the national average. So. All right, good. Let's do the same thing for E then. So E, your Z-score is negative 1.6. So now we want to figure out a salary that's 1.6 standard deviations below 54,166. Good. So what do you think we would do first? It should be the same thing. So the first thing is I want to figure out, and you can either multiply by a negative or you can multiply by 1.6. You just got to know that you're going below, right? So I guess how do I want to do this? Oh, yeah. So we got to figure out what negative 1.6 standard deviations is. So you're going to multiply that by 10,200. So first, go ahead and multiply that really quick. So when you're multiplying those, what do you get? I think you should get negative 16,320. On that. 16,320. Yeah, it should be negative 16,320. So person, a Z-score, a teacher with a Z-score, with a salary Z-score of negative 1.6 means they're 1.6 standard deviations below at 54,166. So notice we have a negative here, which that's automatically going to get us below, right? So I'm just going to then add, just like we did there, I'm going to add 54,166 to that. Because that's a negative, we're really subtracting. So that'll get us below. So now kind of just add those together. Subtract and see what you get there. So what do you get? 37,000. So you should get about 37,846 dollars. So a salary of $37,846. That is negative. That's a Z-score of negative 1.6 or 1.6 standard deviations below the mean. I taught at Temple High School for a year and a half a while back. I know this is a while back. This was 2008. But that's actually the salary. That's basically the salary I started at, was about 37,000. And then I was a geometry teacher. I was a 10th grade teacher. So We made it work. It wasn't a lot of money, but we made it work. All right, good stuff. So given a z-score, you can now figure out this case, but just what data that corresponds to. In this case, salary for a teacher, but you could do this for, again, any problem with any type of data, whatever the context is. So again, that's where I'm saying, notice how useful the z-score is. It's applicable in any context. Essentially, as long as they give you the context and the numbers, you can use a z-score to figure out position and vice versa, to figure out the data from the position. Good. All right. I guess let's do this really quick. So we'll stop and do 16 as sort of our last problem for this little bit. Again, if you get some idea of, we'll get a lot more idea how useful this z-score is as we go on the course, but to give you some idea so far. So we're gonna look at 16. 16 says which score indicates the highest relative position. So notice the question they're asking. So they have an A, B, and C. So A is a score of 3.2 on a test with X. So another way, we've been using this symbol for mean, and that's mean of a population. Same idea. So mean for a sample, they're gonna use an X with a bar over it. So when you see that X with a bar over it, that just means the mean for a sample. So they're saying in A, somebody scored a 3.2 on a test with an average with a mean of 4.6 and a standard deviation of 1.5. There's a second test, probably obviously look at the numbers. It's a completely different test, probably different subject, etc. Maybe not even in the same state, but this person scored a 630 on a test with a mean of 800 and a standard deviation of 200, and a third person scored 43 on a test with mean of 50 and a standard deviation of 5. Good. And a really quick note, notice how I'm reading these. Just get used to sort of reading those that way. Make sure when you're seeing an X with a bar over it, you're saying average or you're saying mean. When you see the S's, again, S's are standard deviation. We've been using this for standard deviation. That's standard deviation of population. For a sample, it's an S. We also saw that in the last lecture. So when you're reading those, read the words, don't just read the letters, so that your head knows kind of what it is and then what to do with it. Good, so these are 3 different test takers on 3 completely different tests, probably different places in the globe. They want to know which score indicates the highest relative position. So which score gives you the highest, so like, again, 3 different tests, but all of the distributions of these tests looks like a bell curve. And so for all of these, we can calculate a z-score, and whoever has the highest z-score, in some sense, so it answers the question, that's the person with the highest relative position, but also that in some sense, that person did the best. So completely different tests, different places, but the person with the highest z-score is, in terms of, if the question is how well did they beat the test, right? How well did they do on the test? The person with the highest z-score is the one that did the best. So the interesting thing is not the person with the highest grade, right? So, what do you call it? If I get a 92 on a math test and somebody who's really good at English gets a 92 on their test, it's like, that doesn't mean that we necessarily are the same smartness or we did just as well as each other, right? Because maybe my math test had a lower mean, so my 92 means I'm a lot higher, right, than the middle person. Whereas on the English test, If their mean was higher, then getting a 92 relatively actually isn't as good. We both still got A's and we did awesome, but it's not as good as, so if on my math test, if I get a 92 and the average is a 72, but on the English test, they get a 92 and their average is an 82, then I definitely beat the average a lot better than they did, essentially. So the way we measure that is our Z-score. So what is our Z-score compared to it? Because then we can look at all, no matter what context or test we're coming from, we can look at our how well we did and compare it with one number, and the Z-score takes care of that. It shows how far we are from the mean. So anyways, so that's what you're doing with this problem. So I wanted to mention that because they give you this A, B, and C. You're gonna have to calculate the Z-score of all of these, but then what you're really trying to say is which one did the best, which score indicated the highest relative position. It's gonna be the person with the highest Z-score. So that's what I'll give you guys time to do. So go ahead and work through calculating the Z-scores for each of these scores. And then let's see who did the best. Pause on your side, I'll pause on my side. All right, sweet. Let's get this calculation going. So let's the Z-score for the first person. They scored a 3.2 on a test with an average 4.6 and a standard deviation of 1.5. So their Z-score is going to be whatever 3.2 minus 4.6 is. So that's their distance away from their distance away from the mean. And then we're going to divide it by 1.5. And what? That's negative 1.4 divided by 1.5. And like we were talking about, y'all are going to round that to 2 decimal places. So what did y'all get for the Z-score there? So for the Z-score, you should have got roughly, this is roughly 0.93. So let's hold on to that. Second person scored a 630 on a test where the average was 800. And the standard deviation was 200. That person's Z-score would have been whatever we get from 630 minus 800. So the distance away from 800 divided by our standard deviation of 200. That is what? Negative 170. 70 divided by 200. Which wouldn't have just been approximate. This one that comes out exactly is sorry, and this should have been a negative 0.93. I'm sorry, guys. So negative 0.93, negative 0.85. So the second one should have been negative 0.85. So, and in terms of, again, in terms of our picture, so now this is no longer the 114th Congress. This is just testing. But in terms of our diagram here, so our first person, their Z-score was negative 0.93, so something pretty close to negative 1. So that's A. All right. Split up here. That's A. Person A. Second person was negative 0.85. So are they closer? Are they farther to the right? Are they closer to 0 or farther from 0? But they're a little closer. So this person relatively didn't do much better. But they did do a little better. So maybe that's person B there. That's negative 0.85, just a little better, a little closer to 0 there. So then our third person scored 43. The mean was 50. Standard deviation was 5. So that's negative 7 divided by 5. And what is negative 7 divided by 5? So the Z-score there you should have got was negative 1.4. So again, let's visualize that result. So where is negative 1.4 on this diagram? But now that's actually a little bit farther out from 0, so that's maybe roughly there. So that's person C. Person A, person B, person C. So which one did the best? Which one had the highest Z-score or highest relative position? That is person B. So person B, again, if this was a race, they did a little better than everyone else. They were a little closer, let's get closer to 0, but I mean, they were just a little farther along that number line to the, going to the right than everybody else. So they were a little closer to the average. So the answer to this then is person B. Person B did a little better than everybody else. By the way, when you take standardized tests, if you've ever thought about it like the SAT, if you think about questions on the SAT, right? So it's just a bunch of questions, 1 through 50. And then you get this score out of it, right? So we were actually talking about SAT scores in the last lecture too. You get a 530 out of it, right? So how did they turn that into a 530? And it actually gets part of that. Basically, they use Z-scores to help kind of turn it into a score somewhere between 200 and 800. So that's what they do, by the way, for whatever raw actual score that you get for your SAT. They transform it into some score between 200 and 800, basically the equivalent score between 200 and 800. That's both for the math section and the reading / English section, language section. So, all right, good. All right, so that'll be enough for Z-scores. I'll leave that as one little part to itself. I'll come back for so this gets you through, by the way, half of about the 3.3 homework. So you can do about half the 3.3 homework from that. And then I'll come back for at least one more lecture. I may split it into 2. I'm not sure. We'll see when we get there. But the next lecture we'll talk about other measures of position. So this is, again, the Z-score is a great measure of position as long as your data is a normal or Bell distribution. But we know that not all data is a Bell distribution. We've seen problems where we didn't get a Bell distribution, right? So what are some ways that we can measure position or figure out kind of the position of data when we don't necessarily have a Bell distribution? That's what we want to look at in the next lecture. So I'll see you guys for that.